didn't take sleep. Okay, Abby.
What's the opposite of
Sober.
As we're doing this, I would like for you to take out you can choose between Desmos or your graphing calculator and graph these.
Can I use
And I'm going to
Desmos
check
on my
around.
phone, or do I need to-
You can use Desmos on your phone or on your device, or you can use your graphing calculator. So we're going to write down our exponential and logarithmic models, and then I'm gonna ask you to graph these. So I'm gonna write down the example graph that you're gonna actually graph, and then I'm gonna write down the general form. So the exponential graph that I want you to graph right now is y equals e to the x in Desmos or your graphing calculator. And the general form is y equals a e to the bx. B is greater than 0 ensures that the exponential growth model has a positive exponent, and the exponential decay model has a negative exponent. So it is supposed to be B is greater than 0 in both cases, because this one doesn't have a minus sign, this one does have a minus sign. But I want you to graph y equals minus e to the minus x.
You! You!
On the Gaussian model, all of this is exponent. You don't have to have a divided by c, you don't have to have a minus b. but you do have to have a negative x squared. So negative x squared, for example, just e to the minus x squared. I want you to graph that.
What does guazzle mean? What is that? What is that word? For the third one.
It's Gaussian.
Oh.
Before we get too far, let me see your exponential growth and exponential decay graphs.
Can I do it on my phone? My computer's not.
Yeah,
It's just for a second.
that's exponential growth and exponential decay. So far, so good. So far, so good. Yep. Mm-hmm.
Well, I do these on
How'd you do what? How'd you do what?
these two.
How'd you do them?
Well, they were,
So what I'm telling you is this is the general form.
Would you grab?
This part is the general form. Where you have the A, B's, and C's. over here, this is a general
We'll
form.
plug it.
So in A, B, and C are just some constants. Here, B has to be greater than 0. This is the one that I actually want you to graph. Where it says example, I want you to graph this one. These three so far.
That
Sorry, what were you gonna ask?
vertical line test probably.
Mr. Shadow, I think Miles broke it.
They don't have to pass the vertical line test.
Jordan, you got graphs for me?
Yeah.
Sharing.
Right here.
We're sharing.
No,
No?
no. I want you to do that. I want you to each do it. Because then you're just watching him do it instead of watching me do it.
We're all
I know, but you're just watching each other do it instead of watching me do it. I want you to actually do it.
Never have you seen this vertical line test passing as this. It definitely passes. But it's just a really big quadratic. And it's hard. It's really just x to the third minus x squared. No.
Okay, logistic growth model in general is A over 1 plus B times e to the minus rx. And the one I want you to graph is 3 over 1 plus e to the minus 5x.
What if I'm running out of colors to use? And decimals, can you create new ones?
I don't know, I don't think you can, but you can repeat colors, or you can unselect your graphs as I come around to show me different graphs. All right, that's 6 graphs.
That's 5. Wait, oh, 6.
Yeah, 5 has 2. Because it's called logarithmic models because you can have log to different bases. And
Oh, wow,
I'm
that's
showing
a lot.
you natural log and log base 10, but log to different bases also works.
This is a piece of art.
Or that's alright.
Do we need to do the number 5?
You gotta do 2 for number 5.
Wait, do we have to do all 4 for number 4?
The examples again are the ones that you're graphing. The ones on the right are the general form. Well, show me your graphs that I'm asking you to graph.
That's a real one. looks so weird. How come you have an orange?
You have an orange too.
Where's my orange?
Just make yourself an orange. You just hold it and bring something to it. That's just so you can get it. Just hold your root here. Just hold your root here, right? No, like you're just so like that. You should already have it.
When we're figuring out which models we can use, somebody remind me of what proportionality models look like. What are the proportionality models that we've learned?
Are those like the parents?
The what?
Like the parents?
No, proportionality. So you've got an x and a y table, or x and f of x table, and you've got 2, 4, 6, 8, and you have 1.1, 1.2, 1.3, 1.4, and you might be asked to say how these are proportional, and then find a constant of proportionality. No? It was the last section. We just did this. This part. Did you forget about proportionality?
Say it again.
Something like x plus 1,
No.
like,
No, I give you a table with x and y,
Yes.
and then I say find a model to show how these are proportional. We had 4 models.
Oh,
Oh.
I'm forgetting it right
Donovan, I want you to use your brain.
now. The
I want you to learn stuff.
Ellen.
Cheat sheet's great. I want you to think about what I'm saying, and well, we only had 4.
Yeah.
We had 2 for 2 variables. We had 2 for 3 variables.
It was the LN.
No, this is before logs.
Oh. I thought you were saying last section like as in the log section.
No,
It's like
no. Last test.
Last
Oh,
big
God.
test.
Last chapter. Proportionality. What are the types of proportionality? Max, what are the types of proportionality?
Direct.
Why don't you just volunteer if you know? Why don't you just shout it out?
What?
I'm asking everyone.
Oh.
Shout it out if you remember. Direct,
Direct, indirect.
directly, proportional.
Oh yeah, direct.
What formula do we use for that?
Y equals
oh my god.
X.
What's the next type of proportionality?
Well, can we do joint proportional?
Inversely proportional. And what model do we use for that?
Y equals 1 over kx or something.
No, k is always just in the numerator. K is always in the numerator.
Then k over x.
K over x. That's the inverse part. Is that it's a 1 over x. What's the next one? Or what are 2 more? Uses in 3 variables.
Joint. Maybe?
Yeah, joint. Joint. That means they're both contributing to directly proportional. So what do we use?
Z
I think
equals
it's
y.
yeah, y equals
X, y? Or no, k,
It's
k, x,
y,
y. K.
Right.
Y equals
K is my constant of proportionality. So k appears in the numerator always. And then so joint means they're both contributing to direct proportionality. So they're both directly proportional. Two things are directly proportional. That's called joint. And then what's the last one?
Inverse, what?
Inverse was when we just had one variable.
Combine.
Yeah.
Combined.
Yeah.
Oh, yeah.
So if we had combined, Then we had z equals what?
K over
KX over Y.
Kx over y. Yeah, so I suppose you could have k over xy, but the models that we talked about and looked at, one was directly proportional and the other was inversely proportional. So x stayed in the numerator, y was in the denominator. Why am I bringing these up?
Because it's gonna refer to something that we're gonna
Because this new stuff that we're doing is kind of along the same lines. So this is different ways of these are different mathematical models. So this is showing how things can be proportional. So either directly, inversely, or even in a more complex way with two variables, they could both be direct. One of them could be direct and one could be inverse. So that's what we did last chapter. So you might have more like I'll give you a table, and it might be more along the lines of this kind of proportionality. It's not proportional anymore. It's a mathematical model. So I'm not going to say proportional, but they are related to each other in one of these ways. And a key to finding which model is going to be a good fit is to find the asymptotes. So let's go back to our 6 graphs, and let's say what the asymptotes are. So you have your 6 graphs here for your 5 exponential and logarithmic models, and let's say where the asymptotes are. Jordan, can you help us out with number 1 exponential growth model? What asymptotes does it have? Yeah. And you might unselect all your other graphs. Yeah, and let's just look at that one.
Okay.
We've talked about this one before.
Okay, so it would go for the number
For
number
equals-
1, it would be x equals 0.
X equals 0 is a vertical line.
Oh, y equals 0, not wrong.
Why is y equals 0 a vertical horizontal line?
Because the only Y value it has is 0.
The only y value it has is 0, so you could you'll have minus 2 0, minus 1 0, 0 0, 1 0, 2 0. All of the different values of x can change. Y never changes. That's what makes it a horizontal line. So the asymptote, the equation for the asymptote is what?
Y
Y
equals 0.
Y equals 0.
I didn't like asymptotes.
I mean,
And now we're back to
Donovan, can you help us out with
2.
number 2?
Well, it's kind of like the same asymptote.
Wait, so there's no vertical asymptote?
It's just
For y equals 0, is there a vertical asymptote?
No.
no,
There's not.
because it keeps growing.
But for you have a horizontal asymptote for number 2 at Y equals 0.
So what is it? What's the chart look like?
The graph.
What's the graph?
It's the inverse or it's the opposite of what you just drew.
Opposite reflected over what?
The y-axis.
Right. So it starts off very steep and then comes down, passes through 0 1, and then approaches what asymptote?
Y equals 0.
Right. Another horizontal asymptote. So this is y equals 0. Miles, can you help us out with Gaussian model? What does it look like?
Would the asymptote be like y equals 0?
Yeah, so it starts off low, comes up to a point, and then and then goes back down toward y equals 0 on both ends. Emily, can you help us out with number 4, logistic growth?
Horizontal asymptote is 0.
What does our graph look like? Hmm?
Looks like this.
Yeah, so at some point it crosses the y-axis, starts off really small, crosses the y-axis, and then goes up to what are the bounds?
3.
So for this one approaches. What is the equation of that line?
Y equals 3.
So y equals 3. Oops.
That's a 0. And then there's 2 of them.
Yeah.
Y equals 0, Y equals
Y
0.
equals 0.
Does this make sense based on the formula for logistic growth?
Yeah.
What if you have a really large number for x, like 5 trillion?
Okay.
Yes.
What if I put what is f of 5 trillion?
3-ish.
Yeah, why? Why do you say that?
It's the asymptote.
Yeah,
It keeps getting closer and closer. And
right.
the trillion, that's pretty close.
So what is e to the negative 25 trillion?
Almost 0.
E to the negative 5 trillion.
Yeah, it's almost 0. Look at e to the minus x here. E to the minus x for a really large number x is getting close to 0. So this 1 plus essentially 0 leaves 1 over 3 over 1. That's where we get that first asymptote from. What if x is really large and negative?
Really large and negative.
Yeah, like if it's negative 5 trillion for x.
It
And
would go
it's
towards
a very big number.
It makes it a very, very big number. So this is minus 5 times minus 5 trillion. So that's e to the 25 trillion. So look at this e to the x. So it gets like really huge, really fast. So then you have a really large number in the denominator. What happens if you have a huge number in the denominator?
You get really small.
It gets really small. That's why it's tending towards 0 over here. Yeah. So graphically we could see that the horizontal asymptotes are y equals 0 and y equals 3, but also algebraically we can see that makes sense for this model. Let's see, Lily, what are the asymptotes for our logarithmic models?
That'd be x equals 0.
Right, because these are just these are very similar to log of x. What's the difference between log of x and 1 plus log of x? So we know what the graph of log of x looks like. It kind of looks like this.
Yeah.
What's the difference between that and 1 plus log of x?
It like moves up 1.
It's a what sort of shift?
Vertical shift.
It's a vertical shift up 1, right? So here's the ln x, here's 1 plus ln x, or ln x plus 1. But it has a vertical asymptote still at x equals 0. What about 1 plus log x?
That's also x equals 0.
That's also x equals 0. So we don't definitively know which model we're going to end up using, but we can narrow it down quite a bit. So if we have y equals 0 as an asymptote, what possible exponential logarithmic models could we be using?
There's 4.
1 through 3. Verse 3. If I have 2 horizontal asymptotes, probably which one am I looking at?
4.
4. If I have a vertical asymptote, x equals 0, which ones am I looking at?
5.
Some variation of a logarithmic model. Right. So we can see those patterns. All right, let's look at an example. Estimates
For what purpose?
of the amounts, open parenthesis, in billions of dollars, close parenthesis, of U.S. advertising spending from 2011 through 2015 are shown in the table.
What's your favorite point on the graph?
Period.
That one's mine. It's like your favorite
Spacing,
point on
yeah.
every graph. It's mine.
So you should make this table in your graphing calculator or on Desmos. Make this table. So we're gonna have
Got lost.
on the x-axis we're gonna show year, and on the y-axis we're gonna show advertising spending. So make this table. 2011, 2012, 2013, 2014, 2015, and 31.3. What does that mean, 31.3?
How do you?
31.3 billion.
It's $31.3 billion. So if the question said how much spending was, online advertising spending, or how much people spend on online advertising in 2011, what would you write your answer be? How would you write your answer?
31.3 billion.
So 31.3 and then I'm done?
No.
Just circle my answer?
No, units.
So what are my units?
Dollars.
Billions of dollars.
So billions of dollars. That's fine if you want to say 31.3 billion dollars. So like newspapers and stuff, sometimes they'll write the dollar sign out front and then the capital B for billion or the capital M for million afterwards. So that's how you could write your answer for that. 45.5 and 49.5. And then you should graph that.
How do you?
Graph your table.
Says that there's like an error in the provided data.
Does it say what the error is? Is it user error? Can I see your laptop?
Probably.
Oh wait, no, I should have said
absolutely good. I can't see anything.
It's like really big.
Well,
Oh,
no,
is
you
it?
just go to 2000.
Oh, is that 2000?
Because you plotted that point for x.
Oh my goodness. Okay, there it
What
is.
did you expect? Just a not show.
Oh, I was expecting to see it. I didn't know where it was at. Oh, it's not big. It's just really far.
No, it's not. It's not big. It's just a little further. Drop something.
Yeah, I can tell.
Drop something.
And just the feed and the fact if I drop something. Oh, I think there's not this one. What are you doing? Are you ready?
I don't know. It's plotting your data.
Yeah. Okay.
Mm.
Alright, thank you.
All right, let's see your plot. What is this plot called when you have just points like this? It's got a plot.
It's got a plot. You do the plus, right?
Yeah, what you do is what you do is you get distracted with doing other stuff, and then
Yeah.
you wait for me to come around, and then you say, "Oh, how do I start now that Mr. Sable's standing right behind me?" Yep. Oh, look at that.
I taught this dude like
That's
3
interesting.
times.
Oh,
I had to change this.
The
Changes to
changes,
2011,
and he still hasn't
2012,
fixed it.
2013.
Do you want to
No,
know the best part? Do you want to know
because
the best part?
that's one difference I can spot between yours and CC's.
We kind of
It's-
put it on the same.
Bro, it's funny too, because if we break it up in class, we can literally make the excuse that he has to push it back. Because
No.
he didn't like the
I didn't know this was
Don't even look at Google Classroom.
Just
Google
give us
Google Classroom is it's like
It's
completely
linear,
destroyed.
but it won't.
It's completely messed up. It's completely wrong.
What
What
do
do
you
you
do?
do?
Can I see
He
laptop?
fixed it. He fixed it. He fixed it.
CC, can I see it too?
Never mind. We're seeing what we're seeing.
Try to scrutinize this.
Okay,
So
so
what
is going on?
But that's not.
Mine's not that smart.
tell him that.
You have a MacBook Pro.
No, we all had. No, it wasn't just you.
I don't really like
Yes.
Macs.
Oh.
So like it doesn't say it's due, so I don't think much it's like make it just like yeah, I was like really it was like yeah, it said it was due like last week.
No, it was due like Friday or something.
Yeah, that's what it was.
Classes after this?
Dude, just doing a correction problems.
Perfect regression.
2011,
Just doing
2012.
Enter correction problems you can get from pages of it. It's
I'm just gonna put the data in until I get an error.
Mm-hmm.
31.3, 36.8,
I mean, the spacing is so stupid.
41.2,
Check the spacing. This is
45.5, 39.5,
I'm talking about like
and then I can use the linear regression button. It does it. And so, what I like to do is come over here to the gear, I mean to the wrench, and I can manually tell it, X is gonna go from 2010 to 2016, and Y is gonna go from 0 to 50. That way I have everything on my.
Nice.
So you were getting an error, and I don't know what it was. So So just as a troubleshooting step, I went through and deleted data until an error message went away. It never went away. I came up here and I deleted the whole table. And started again, and was watching for any error messages because CC put in the exact same data that you
Right.
did, but you had an error. Where it came from, I don't know. Maybe you hit a stray key accidentally, and there was a character that it just didn't show.
Yeah.
So by starting over and putting the data in, even though that was, an extra step, I was able to
Thank you.
avoid the error message.
That's
your scatter plot?
Yes.
Right.
Oh, sorry.
You okay?
Hit my knee.
Oh.
Was it the funny bone in your knee? 'Cause that sucks.
All right, continuing on. So our scatter plot basically looked like this. So if you want to just show part of your data, you can draw your map like this, draw your graph like this. I mean, if I don't want to go all the way down to 0, a squiggly line here shows the reader that I'm cheating a little bit. So I can have 2011. Obviously, this is not from year 0. This is just 2011, 2012, 2013, 2014, 2015. And the squiggly lines show that I'm just showing that part of the data. So this is about this. That's something like how your graph looked.
In the grand scheme.
Sure. It was like the amazing thing.
Something like that, yeah. Mouse, close your laptop. Take notes. An exponential growth model that approximate the data is given by So here the model that we're going to use uses 11 to count for 2011 and 15 to count for 2015, and this is where S is spending in billions of dollars, and T equals 0 represents 2011. So can you graph this and see how this compares to your data?
Is it 9.3 E?
9.30E. Yeah, 9.3.
Okay.
That's 5 or is that S? In the beginning.
That's
S.
Okay.
The variable S is spending.
Yeah.
Was it pretty close? Lily, what'd you say? Oh wow about?
No, it was just I did it weird, so it showed up really weird. What's pretty close?
The comparison. So we have the year we have the actual advertising spending, and we have S, the amount of spending given by our model. So if you put in, if you put in 11 to this formula, what do you get?
When you put in 11,
If you put in, what is S evaluated at 11?
31.3.
No, that's the actual number.
Oh wait.
So for
What is S? What is S at 11?
If I unselect it,
11.
Yeah.
so like these are practically the same.
I want you to figure out what S at 11. We're gonna fill out this table.
But,
Miles, what are you doing?
Filling out the table.
Mr. Shin. No,
Oh,
it's not
wait.
on your graph.
Hmm?
It's not on your graph.
Also, like,
Just replace S and G with Y and X.
Okay.
Why is it written such a weird way?
What do you mean? What's
If
written?
you do an exponential regression with log mode on, then it gives a similar one that's 9.30 times 1.11x or 1.112x, which is very similar to that. The numbers 9.30 and 0.112 are the same, but it's just two terms multiplied rather than e to the.
Did you do a linear regression?
Yeah, but I made it log mode, so the numbers are the same.
Well, you did a linear regression. So it's two numbers. It's giving you a straight line regression. It's giving you a straight
Or
line.
not a linear, exponential, my bad.
Did you do exponential?
Yeah, and it's giving the same numbers
But with
there,
but with
in a
log mode
different-
on?
Well, it's in a different like form. Here, I'll show you.
I understood.
It's
I understood.
the same graph. It's just like why is it multiplied like that instead of e to the?
It's more accurate that way. If you look at like the R squared, it shows that it's closer to all the points.
Well, that's just because the numbers are more accurate. I mean, like the form of how it's written out. Because
So I want you
clearly
to think about
they're
about why these are both called exponential. So these are both examples of exponential. Logarithmic. What's the difference between these two?
they have like different shapes. Like they go different places at different points.
What's the difference between these two models?
That one of them just has a different log base.
It has a different log base. So these are two different logarithmic models. So for exponential growth model, the same thing could apply here. So instead of saying base E,
Mm-hmm.
we could have base 2, we could have base 1.198, we could have base 10, and it's still an exponential growth. This is just choice of base E, just like this is log model, choice of base E, this is log model, choice of base 10. Just because they're convenient to work with, but you could have any base, you could have any log base, and here you could have any exponential base.
Okay.
So it's giving you an exact number raised to the x. And what we're doing here is we're giving an exact base raised to a power.
Okay.
So it's still exponential. All right, so we are putting in t values of t. Cece, could you give me s at 11?
11?
Because this, are we supposed to put it, so for our model S, are we supposed to put in 2011 or 11?
11.
11. So we need to put in S of 11 equals what?
31.3.
No, that's the actual data. That's not S of 11. That's not our model. This is what we're this line here is actual data. This is what we're trying to model, but that's not what you get when you put in 11 into this model. What happens when we put 11 into this model?
How do you put 11 into the model?
Use your calculator.
You just put the calc in and it's you get no, I won't say it.
How are you doing in the Desmos, Jordan?
Oh, well,
it's like
just,
10
We have a
something.
butcher.
I'm just doing it
10
like,
point.
I hope it's not. I hope it's close to 31.3.
I put it like that,
I got
32.19 or something, 19.
Just put 11 in for.
Show that to CC,
Okay.
please. Thank you.
CC. Alright, so ignore the top part, just focus on this.
I got 32.19.
Yeah.
Yeah, I
Yeah.
got 32.198.
Okay, so we're just doing to one decimal place. So let's round it one decimal place. CC, let me know what you get.
Did I put something wrong with the?
You might have.
Keep that.
Just make sure you
can just add that equation of x equals 11. So it shows what it equals.
Oh, yeah. Mine's 32.
Make it x equals 11.
Well, my equals 2.
Okay.
I'm not trying to give you a hint. I'm not trying to get your attention. I'm trying to actually clear my throat.
It's not like
Yeah,
you're,
just make it x.
it's not like you're like.
Emily, what'd you get for S at 11?
And then the great job with a cross.
Oh, it becomes a graph and do it like
No, it's not. You just.
that. Okay.
Emily, you're not tracking with what we're doing. I want you to keep up with what we're doing. Miles, what'd you get for S at 11?
I got something.
I'm trying to figure out how to copy this down.
Don't go on sidetracks.
Is this the
Miles, I need you to stay with what we're doing.
Is this 32.2?
Wait, you said S equals 11?
32.
S at 11.
S at 11.
Yeah.
32.19.
We're one decimal place.
32.2.
CC, is that what you got?
Yes. 32.
Max, what's the S at 12?
Well, let me. It's 36 point. It's just 36.
To one decimal place?
Yeah. It's 0.0.
Yep. Emily, what'd you get for S at 13?
Hang on. Sorry.
Oh, wait, yes. Oh, okay, so, yeah, S is at 1, yeah.
And then,
It's all decimals. Right,
and then.
perfect.
40.4.
Sorry, what?
40.4.
Yeah. Is that what you got, Donovan? Lily, what'd you get for S at 14?
45.2.
And Miles, what'd you get for S at 15?
50.6.
50.6. So you can see the comparison here. It's pretty close.
Yeah.
The predictive model, the predictive accuracy of the model is pretty good. All right, so here's the question. That's all preliminary. Here's the real question. Is it possible for us to answer when the U.S. online advertising spending will reach $80 billion?
Yeah. Yeah. Yeah, yeah.
Why do you say yes? Does anybody say no?
Wait. What does S stand for?
Spending.
This is spending. So this is our these points are our actual data, and then the line is our model.
Because this is
And
in.
what's
Could you
the
put
question?
the 80 billion
This is
in
4
for
billion. This is
S
8 billion.
in the equation?
Yeah.
Yes, you're already solving the problem. I'm asking conceptually,
Oh, okay.
could I use this model to, I want you to hear this question. I want you to hear this question. Could I use this model to answer when, at what year spending was $40 billion?
Yeah.
Yeah.
Could I use it for 32?
Yeah.
Yeah.
Could I use it for 50?
Yeah.
Could I use it for 80?
Yeah.
Yeah. It's in 2019.
Yeah.
I'm not asking for when it is, I'm asking conceptually, can I look outside my data?
Yeah.
This is what I have for data.
It won't be as accurate, but it looks.
You can't.
So-
you can't
so-
do that.
It might not be as accurate. So we have a model that corresponds
No,
pretty,
It's in a lot of years. Actually, no, it's in a.
CC and Max. I'm trying to tell you something conceptually here.
Yes.
So, do you know the name of the, everyone close your laptops. What do you call this when you have data and you're trying to get an accurate number inside your data? Hmm? Do you know? Do you know the answer to that? What do you call that? What do you call that? Hmm?
Have we learned it?
Not in this class. I wondered if you know it from outside this class.
Probably not.
So there is a type of like, I guess it's an aspect of data science where you're using your model to predict points inside your data, emphasis on in.
Yeah. You've mentioned it, but I don't remember.
Oh, did I can't remember if I mentioned it in here.
Yeah, you talked about
Analyze.
it.
In.
Cause
Analyze?
analyze.
Look in the
Nailed
data.
it, Miles. Intelligence. Oh,
Intellectual.
interpolation.
Interpretation.
So we're going to, so within the data points of 2011 to 2015, we can interpolate our data and have a high degree of confidence that based on this model that we're going to get a really accurate number. Like if I wanted to say when was spending or when will spending be 80 billion? Instead, I'm no longer interpolating.
That would be, that's outside the graph, isn't that? Would that be outside the thing?
Extrapola.
Extrapolation.
So
That's a perfect table.
So yes, some of you are already jumping to the method of using this model to extrapolate our data. So I've seen, I can't remember if it was this class, but I've seen people answer like on labs, can you use this data? That's why we're starting with can you? Is it even possible? Can you use this data to answer when spending will be $80 billion? Yes. It is an estimate. So it's based on the model. You're predicting when you think $80 billion will be. Yeah. It doesn't mean that it ends up being that way. That's just the way this model that does a pretty good job of representing our actual data. If you extend that out to the 80, right? So how do you do it? Sorry, what?
So what you're saying is that you don't want like the number, you just want yes or no?
No.
Or do you want
I want
that?
the number. I want the number, but before we get to the number, we have to ask ourselves, is this even possible?
Oh, right.
So if the data was
I needed to write that down.
all over the place, or our model didn't do a good job of predicting, we wouldn't have a high degree of confidence. We could still plug in, like where would we put in the 80 to solve it?
For the 80,
You
which
can put
80
the
would be
T.
20, the year 2080. If it's T, it would be 2080. We're
So
not
you
asking
put
what
in
happens in 2080. We're
You
asking
put
when
in-
is
You put in
spending
as
80 billion.
as the spending.
S, 80 is S.
80 is S, that's spending.
Let's do that.
Oh, and then we're solving it like the.
Yeah.
Put S as 80.
So 80 is S. So here, 80 is S.
Take this off.
So I'm going to write 80,
Are you gonna want us to isolate safety?
9.3. Yeah.
Yeah, that's what. Yeah. Well, I assume so.
Which you can totally do, right?
Yeah. You could, like definitely not like what you just taught us.
Yeah, so this one actually up here, this one actually is the original equation. This is sub 80 for S. How do I solve from here?
So from, divide by 9.3.
Divide by 9.3. I'm just going to do this. I'm just going to do this in fractions so far. I'm not going to resort to my calculator yet.
And take the ln.
ln of both sides. T equals what?
No idea what that is. Put that in my calculator.
This is inverse property.
T equals natural log 80 divided by 9.3 all over 0.112.
Right.
Is this just like basically PERT? Like is this?
It's very similar to the it's very similar to the exponential or the continuous compounding
Oh.
financial formula.
Yeah, that's what it was. It was because you put this on the quiz essentially, like this part of it.
What does T end up being?
Let me divide it.
19.1.
And that
19.1.
so our answer from the formula is 19.1, but that is not our final answer.
Because it was T is the year
2019 in January.
So it'd be 2019.
Yeah, the point one doesn't really correspond to January because there's 12 months.
Yeah.
But
Oh.
so the answer is in year.
You just put it in years.
What's the year?
2019.
2019.
Somewhere in 2019.
Right. Yeah.
I think somewhere it'd be
Beginning
like,
of it.
Yeah.
it'd be like January, February or something.
Awesome job, y'all.
Yay.
Hey.
I have a topic question. So, like, is like the amount of square numbers equal to the amount of like counting numbers?
I'm like